So recently, we've started this new chapter, linear model selection and regularization. And we had a look at, was it two algorithms? I think I need a quick refresher. So we had best subset selection. And how did this algorithm work? You have P predictors. And you're going to look at the fit with no predictors, and then take, when k is 1, you'll take each of the P models with a single predictor. When k is 2, you'll take each of the P choose 2 models with 2 of the predictors, the first 2, the second and the third, the last 2, the first and the last. And you compare models. Initially, you compare models with the same number of predictors. And this is step B. And we're measuring the best based on the smallest residual sum of squares. And the best model is assigned the label MK. And what do we do with these MKs? Well, you have M naught. This is always the same one. There's no choice. It's just with no predictor variables. This also will always be the same model. It's just with all the predictors. Everything else in between, you're choosing the best one. So in Pascal's triangle, there's only one choice of using no predictor variables. There's only one choice of using all the predictor variables. But in step 2, you have selected, the best from, one second, I'm coming. Sorry about that. In step 2, you have then selected the best model with a single predictor variable, the best model from those with 2 predictor variables, and in this way, you've built a set of P plus 1 models, ranging from no predictor variables to all the predictor variables. We then compare between these using one of the diagnostics, such as what we saw in chapter 5 with cross-validation. And there are also some other diagnostics which we haven't really gone into at this point in the book. There were times where they did come up, but we may have glossed over them. But there is the K-key information criterion. There's the Bayesian one. And there's also adjusted R-squared. So this is best subset selection. It is a type of subset selection. In this chapter, I seem to remember there are 3 types of distinguishing or comparing models. We've started subset selection. There is also shrinkage, where we minimize the betas to 0. Maybe I shouldn't use the word minimize, but we shrink them to beta, to 0. And there's also dimension reduction. And we'll be seeing these in today and in future sessions. Okay. And another way of performing subset selection, and what is subset selection? It's where you're taking out some of the predictor variables. You aren't using the full extent of data available to you. Now, best subset selection, as you can imagine, takes ages. If there are 20 possible, if your data set has, besides the column of data that you're trying to predict, so that's the response variable, if it also has 20 separate fields, each field containing historical data on a particular characteristic of the data subject. That data subject could be insurance policyholders, it could be companies quoted on the stock exchange, it could be patients, you name it. If you have 20 of those fields and you try using best subset selection to determine which of those 20 one should use, then that would require 1 million fits, which it's going to take quite long, isn't it? 1 million fits, and then you have to compare them, etc., etc. Instead, and we can start reading, for computational reasons, best subset selection cannot be applied with very large P. Best subset selection may also suffer from statistical problems when P is large. The larger the search space, the higher the chance of finding models that look good on the training data, even though they might not have any predictive power on future data. Quite right. The more predictor variables we have, it might be just the case that by random luck, you've from all the different, Pascal's triangle, from the 2 to the power of P different models, the larger the P, the more of these models there are, the higher the odds are that just by random chance, one of them would look like it's doing a really great job, but it would simply be by sheer luck. And in fact, the book goes on to say, thus, an enormous search space can lead to overfitting and high variance of the coefficient estimates. And remember, what we want to avoid is overfitting. What we want is to reduce the variance of a model. There's always that trade-off, the bias variance trade-off. Okay. So instead, we seem to be, and this is where we had arrived last time, we have forward stepwise selection. And let's see if we can make more sense of it today. Forward stepwise selection is a computationally efficient alternative to best subset selection. While the best subset selection procedure considers all 2 to the power of P possible models containing subsets of the P predictors, forward stepwise considers a much smaller set of models. Forward stepwise selection begins with a model containing no predictors and then adds predictors to the model one at a time until all of the predictors are in the model. In particular, at each step, the variable that gives the greatest additional improvement to the fit is added to the model. And here we have maybe a more formal explanation. Let's have a look. So we start in the same way as best subset selection. You start off with a model that allows for none of the characteristics within our observations in the sample data. Now, we have a loop over here, and it takes, as a first iteration, when k is 0, we consider all, so this would just be p models that augment the predictors in mk, so m0, with one additional predictor. Choose the best among these p minus k models and call it mk plus 1. Here, best is defined as having the smallest residual sum of squares or highest r squared. Right. So we're looking at p models over here. At least step 1. Step 1 is looking at uses p models. Okay. What about step 2? What about step 2? So step 2 is when, should I call it step, like iteration, loop. So now k is 1. So this was when k was 0. This is when k is 1. And it uses p minus 1 models. Which p minus 1 models? Consider all p minus 1 models that augment the predictors in M1. Can't really say I'm following. Which predictor variables are we using now? That augment the predictors. So this would be M1 with one additional predictor. Oh, wait a minute. Oh, I think I know why it's p minus 1. Because you've already picked. So to create. So step 1, when k is 0. Step 1, when k is 0, you compare p models with one predictor and choose the best, calling it M1. That means that now you've selected one of the predictors. So now in step 2, you've chosen the best in step 1. So you've chosen a parameter. If it's, I don't know, it's a model predicting how well students do in their exams. You've chosen, for instance, and if you have p characteristics, you've chosen, for instance, the number of hours they do studying every day. So that has been selected now. So when you come around to performing this again, you've already selected one of the predictor variables. And now it's time to choose another predictor variable from the remaining p minus 1. So you would create P minus 1 models. Let me tell you which P minus 1 models. Just going to excuse me. Right. So for instance, this best one, this so-called best one. Let's say we chose with parameter let's call it parameter A. Parameter A from the P parameters. Now which models are you going to compare? You're going to take A, you're going to take as a on what we're regressing. So in step 2, you're going to look at models with two predictors. Two predictors, it would look like visually, you can imagine this. You have your data. You're going to fit some kind of plane. In step 1, we've decided to use A. And now the question is, which one do I take over here? But I can now only choose from P minus 1 since A has already been selected. So you'll try, you check, and finally you decide to maybe include, maybe we don't call it A because A really gives the wrong impression. Anyway, I'll keep it A. Hopefully I'm doing a good job of explaining this. So uses P1 models with two predictors, A, and everything except A. I'll just do it A asterisk. So I'm just using A asterisk to be a second predictor that isn't A. And choose the best with parameters, this time, for example, A and B. And now this is your second model. Now the question is, when do you stop? Because I think there must be a point where you kind of say adding more parameters doesn't really help. No, apparently, no. So you do this, you perform it P minus 1 times. Why P minus 1 times? Well, if you calculate, let's say you come to the very last one. How many models then? You have P minus K, but K is P minus 1, and that just becomes 1. So in the very last one, in this loop, you will add the final variable, the final predictor variable, and you can only, there's only one to consider, and you calculate the RSS. That would just be the full extent. That would be the model where you're using all the predictor variables, all P of them. So that's it really, and hopefully realizing how much quicker this is going to be, because you'll only create how many times is this performed? Well, there's M naught. Let's say that we had 20. Let's say we had P is 20. Let's say P is 20. So for M naught, you do one fit, not using any of the predictor variables. And then when K is 0, you do 20 models. And then, unlike Pascal's triangle, when K is 1, you do 19 fits, 18, 17, 16, all the way to the last one. When over here, you're fitting all the variables. So you calculate. So for M naught, there is no choice. It's just one. Assuming P is 20, when K is 0, there are 20 models to compare. The model that only uses the first predictor variable, the model that only uses the second predictor variable, until the model that uses the 20th predictor variable. When K is 1, you now have 19 models. You get the one that you chose over here. That's the difference between best subset selection and forward stepwise. From the one that you've chosen over here, so you choose one. You choose one. You're making a choice over here, whereas in best subset selection, you don't use a previous choice for the next choice. But the one that you choose over here, the one predictor variable that you choose over here, you will then use it in each one of these 19 models together with another parameter. And again, you choose one. You choose one. Which one do you choose? You choose that predictor variable that, together with the previously selected predictor variable, gives you the smallest residual sum of squares. If this needs repeating, I know I'm not doing the best job. Please just send me a chat, raise your hand or unmute, and I'll be very happy to elaborate on this. But just for the last time, I mean, it's not like a majorly difficult concept, but it is the first time that we might be thinking along such lines. M naught is the model with no predictor variables. You are not looking at any of the characteristics. If it's the emergency room data, you ignore all the symptoms, not looking at any symptoms. When you then enter step 2 and this loop starts, assume that we have 20, assume that we have data on 20 types of symptoms, heart rate, levels of consciousness, you name it, tiredness. You fit the response variable on a single predictor variable, and you do this 20 times. So you look at each predictor variable. From those 20 models, you calculate the residual sum of squares, which uses actual versus expected, and you choose the best one. Let's say you chose heart rate. So heart rate as a standalone predictor variable, heart rate gives you the best residual sum of squares in terms of predicting if it's a stroke, if it's a seizure, if it's an overdose, you name it. Once you've selected heart rate, you create 19 other models with heart rate and one of the other not yet selected predictor variables. Again, you choose one of them based on the residual sum of squares. And you repeat this process until finally you create the model with all the predictor variables. So you would have chosen one over here, and up to this point, up to what I've shaded, you've selected all of them, with the exception of a single predictor variable. You include that one as well, and there's, you have no choice. Yeah, you include the remaining one, so there's only one such model, and there is no choosing over here. There's nothing to choose. You just calculate you calculate nothing. Then for each of these models, for the model with just this one predictor variable, for the model with these two predictor variables, until the model with all predictor variables, you calculate either the cross-validation error, the AIC, the BIC, or the adjusted R squared, and you select the best model based on one of these diagnostics. That's it. That is forward stepwise selection. And it's P minus K models because you've always, P minus K is telling you, you've already selected K predictor variables previously. Now you're going to include an additional predictor variable. Okay. Unlike best subset selection, which involved fitting 2 to the power of P models, forward stepwise selection involves fitting one null model along with how many? P minus K models in the kth iteration, where K is 0, K is 1, until P minus 1. This amounts to a total of 1, that's the null model, plus these P minus Ks for these iterations. And if you do a bit of algebra, you shall get this. And let's have a look. So it doesn't vary exponentially with P. It only varies quadratically in P. You have a quadratic effect going on over here. This is a substantial difference. When P is 20, best subset selection requires those 1 million models that we mentioned earlier, whereas forward stepwise selection requires, and this is like 4 magnitudes less. And there's also a footnote. Though forward stepwise selection considers so many models, it performs a guided search over model space. And so the effective model space considered contains substantially more than these models, which simply means guided is that you're always choosing the best one and then you're using it for the next one. So it's not like we're ignoring these 211. It's not like we're only looking at these and ignoring the rest. We're taking these 211 because there's a direction. Think of this as at secondary school would speak of trial and improvement. Sometimes we accidentally refer to it as trial and error. Trial and error sounds like unguided, right? You randomly not each time. It doesn't feel like, you know, trial and error, like you're not learning from the previous. But when we describe it as trial and improvement, it just the phrasing of such an approach endows it with a sort of direction. In step 2, part B of the algorithm, we must identify the best model from among those P minus K that augment MK with one additional predictor. We can do this by simply choosing the model with the lowest residual sum of squares or the highest R squared. However, in step 3, we must identify the best model among a set of models with different numbers of variables. This is more challenging and is discussed in section 6.13. This is when we start talking about the AIC, the BIC, forward stepwise selection's computational advantage over best subset selection is clear. Though forward stepwise tends to do well in practice, it is not guaranteed to find the best possible model out of all 2 to the power of p models containing subsets of p predictors. For instance, suppose that in a given dataset with p equals 3 predictors, the best possible 1-variable model contains x1, and the best possible 2-variable model instead contains, right, x2 and x3. So that's the drawback of forward selection, that once you've selected a predictor variable, you then have to use it. Then you've already selected it, so it's going to appear in that. Then you add a second variable to it, or you include a further predictor variable, and then you include a further predictor variable. What happens is that it may very well be the case that while in the context of a single predictor variable, maybe x1 is the best, it may very well be the case that if it's a 2-variable model, x2 and x3 actually give you the best, the lowest RSS. Then forward stepwise selection will fail to select the best possible 2-variable model, because M1 will contain x1, so M2 must also contain x1 together with 1 additional variable. It's just the way forward stepwise selection works. Table 6.1, which shows the first 4 selected models for best subset and forward stepwise selection on the credit dataset, illustrates this phenomenon. Let's have a look. So this is table 6.1. Once you've picked rating, no, excuse me. Let's look at forward. Once you've picked rating, it's going to appear in each of the following iterations, where apparently you would then add income, and then if you're going to include 3 of them, you would add income and student together with rating. Whereas in best subset selection, while you would initially pick rating and then rating and income, and then rating, income, and student, when you come to picking 4 variables, apparently rating isn't that important. The information in rating might kind of correlate in any case with perhaps income and limit, and then it's better to drop rating. So what we're saying is this red compared to this pink, the red is actually better than the pink. It is better to have cards as opposed to having rating. Now, might be a minor difference, so it might not make the impact might be minimal, but these are things that can happen. Table 6.1, which shows the first 4 selected models for best subset and forward stepwise selection on the credit dataset, illustrates this phenomenon. Both best subset selection and forward stepwise selection choose rating for the best 1-variable model, and then include income and student for the 2 and 3-variable models. However, best subset selection replaces rating by cards, and that can never happen in forward stepwise selection. There's never going to be a replacement. Once something has been picked, it's going to appear in all subsequent augmented models, augmented by a single, each time augmented by a further predictor variable. While forward stepwise selection must maintain rating in its 4-variable model. In this example, figure 6.1 indicates that there is not much difference between the 3 and 4-variable models in terms of RSS. Really, but I'm not seeing RSS in table. In this example, figure 6.1. Figure 6.1. And where is, here we go. No, that's figure 6.2. Oh, right, this one, right? Figure 6.1. Okay, in any case, there's not much of a big difference between 3 predictor variables and 4 predictor variables. Figure 6.1 earlier indicated that there is not much difference between the 3 and 4 variable models in terms of RSS, so either of the 4 variable models will likely be adequate. Adequate, okay? Forward stepwise selection can be applied even in the high dimensional setting. High dimensional setting is when you have many, in inverted commas, predictor variables, where the number of observations is less than the number of predictor variables, which is very rare, right? I mean, if you're looking at an insurance data set and each observation is a policyholder in a specific year, and there's a really, I've been teasing this recently, once we get a few more chapters, and we're actually halfway through. This isn't a very long book; it's only 400 pages, and we're on page 200 and something, low 200s, but definitely halfway through. Although it doesn't mean that it's not going to get harder and that it's going to take us longer to finish 10 pages in a few weeks' time than it's currently taking us to cover the same amount of volume. But once we finish this book and we move on to think of it as more typical actuarial work, at least within an insurance context, and that's where you usually find the majority of actuaries, at least till now. That doesn't mean that there are, one hears of these like non-traditional roles. Could be at insurtech, fintech, could be banking. Really, it is a Swiss Army knife in terms of the skills that the qualification enables you to bring to the table. We will look at policy. We'll look at a database with, for instance, 500,000 observations, and each observation will be a specific policyholder in a specific year. So, for example, think of all the policyholders insured with company XYZ over the calendar year 2020. And normally what's the case is that you have 500,000 policyholders, and then maybe you're going to look at 40 characteristics, 50, 100, 200. It doesn't get more than that usually. However, nowadays with there's something called telematics. So, for example, telematics could be if you're doing some kind of physical training and you have your phone on you, it could very well be the case that it's monitoring hundreds of different features within a specific session, gym session, for instance. Same thing with telematics. So think of, for example, electric cars. And in fact, Tesla, I don't know the details, but It's actually quite specific to our own jurisdiction. There is they definitely do have something in our own country when it comes to insurance, but the car, um, it's no longer our parents' car, which isn't sending any data to the manufacturer, but now it is an electric vehicle. It's connected the entire time to some kind of internet signal, Wi-Fi or Starlink, satellite internet service, and it's sending out data, well, the entire time. Or if you're on social media, the data it's collecting, even if you don't click someone's post, but it does measure, it does collect to a certain extent how long maybe you spent looking at that post. So when you're scrolling on your phone, on your laptop, and you pause to look at it, but that's sending out signals to the company behind whichever platform we're using, that it was of interest to you. Now whether it was of interest to you because it was controversial, because it touches on issues that you might be interested in, for example, just education, politics, social issues, you name it. And this is where you could really end up with the number of predictor variables still. We'll see if this book ever really goes into. Intuitively, I would say this is a very rare situation. Definitely not something I've ever come across in my own professional work, where the number of predictor variables is greater than the number of observations. Now, what we say is, however, in this case, it is possible to construct sub-models, so many, only, since each submodel is fit using least squares, which will not yield a unique solution if p is greater than or equal to n. So meaning you would only take up to n-1 predictor variables. You wouldn't use all of them. Whereas we're kind of implicitly assuming over here when we write MP that you have more observations than you have predictor variables. Not too important. Let's move on to backwards stepwise selection. I guess this is probably going to be the same, but instead of adding one, you maybe take out one each time. Like forward stepwise selection, backward stepwise selection provides an efficient alternative to best subset selection. However, unlike forward stepwise selection, it begins with the full least squares model containing all p predictors, and then iteratively, so that's your step 2, where you see the word for, removes the least useful predictor, one at a time. Details are given in this algorithm. Can't be too difficult to understand this, right? It's the same principles. Only difference is that it considers all k models that contain all but one of the predictors in MK for a total of k1 predictors. Like forward stepwise selection, the backward selection approach searches through only so many models, and so can be applied in settings where P is too large to apply best subset selection. Also, like forward stepwise selection, backward stepwise selection is not guaranteed to yield the best model containing a subset. This is the price we pay of the P predictors. Backward selection requires that the number of samples n is larger than the number of variables p. Again, not too important, but apparently this is an advantage of forward stepwise. You can use it even when you have more predictor variables or more potential predictor variables that you may consider in your final model than you have observations. Right. There's also something hybrid approaches. Let's just quickly read through it. The best subset, forward stepwise and backward stepwise selection approaches generally give similar but not identical models. As another alternative, I don't imagine this book is going to go into them, but hybrid versions of forward and backward stepwise selection are available, in which variables are added to the model sequentially in analogy to forward selection. However, after adding each new variable, the method may also remove any variables that no longer provide an improvement in the model fit. Such an approach attempts to more closely mimic best subset selection while retaining the computational advantages of forward and backward stepwise selection. Choosing the optimal model. So this is now step 3 in each of these 3 approaches: the best subset, the forward stepwise, and the backward stepwise, where we're going to do either cross-validation or something along that same kind of approach. So, best subset selection, forward selection, and backward selection result in the creation of a set of models, each of which contains a subset of the P predictors. In order to implement these methods, we need a way to determine which of these models is best. As we discussed in section 6.1.1, the model containing all of the predictors will always have the smallest RSS and the largest R squared, since these quantities are related to the training error. Instead, we wish to choose a model with a low test error. And I'm sure you know all these things, but even just for myself, what we're saying is, remember how least squares works. Least squares works, it picks the parameters, the model fit that give the smallest RSS. So now we need something else. Now we need a model with a low test error, as is evident here, and we show in chapter 2. The training error can be a poor estimate of the test error. We had seen this. We could very, very quickly. It was these first diagrams. Do you remember these? Red was training, mean squared error, whereas blue is the test. You're using it on observations that have not been used to train the model. Training the model just means fitting the parameters. And what happens is that usually the more flexible the model is, the more it's allowed to follow the observation data the more closely it's allowed on a more granular level, then although it's going to give you a pretty good mean squared error, when it comes to the test error, it doesn't usually perform that well. This is the problem with overfitting. This is why we need to avoid overfitting. This is why we want to minimize the variance. The higher the overfitting, the more we have overfit, the higher the variance. Okay. Therefore, residual sum of squares and R squared are not suitable for selecting the best model among a collection of models. with different numbers of predictors. In order to select the best model with respect to test error, we need to estimate this test error. For each model, right? We are on the same page, I hope. Each of these algorithms, let's find one of them, gives you the best model with no predictor variables, the best model with only a single predictor variable, until the best model, and there'll only be one such model. It's not really the best, but it's with all the predictor variables, with all. So if it's the emergency room and you have your doctors and your nurses, your medical staff diligently listing, measuring, recording 20 symptoms for each patient, then MP is the model that uses all 20 predictor variables. Now, very often you will not need 20 predictor, you will not need the whole set. Look at, for example, this one. This one, it was based on the credit data. Once you've taken Once you've taken 3 from these 11 predictor variables, you've already, from that point onwards, adding more predictor variables does not really improve the residual sum of squares, at least not on average. In order to select the best model with respect to test error, we need to estimate this test error. There are 2 common approaches. We can indirectly estimate test error by making an adjustment to the training error to account for the bias due to overfitting. Okay, interesting. I don't know what that is referring to. We can directly estimate the test error using either a validation set approach or a cross-validation approach, as discussed in Chapter 5. We consider both of these approaches below. Now, let's see if we're going to get caught out in what these things actually mean. So we showed in Chapter 2 that the training set MSE is generally an underestimate of the test MSE. Recall that MSE is equal to the residual sum of squares, so it's the mean. The residual sum, you're summing, that's your numerator, and then you are dividing by the number of observations. This is because when we fit a model to the training data using these squares, we specifically estimate the regression coefficients such that the training RSS, but not the test RSS, is as small as possible. In particular, the training error will decrease as more variables are included in the model, but the test error may not. Therefore, training set RSS and training set R squared cannot be used to select from among a set of models. Okay, so just repeating what we read over here. So, however, a number of techniques for adjusting the training error for the model size are available. These approaches can be used to select among a set of models with different numbers of variables. We now consider 4 such approaches: CP, AIC, BIC, and adjusted R squared. Figure 6.2 displays CP, BIC, and adjusted R squared for the best model. Remember those M0, M1, M2? for the best model of each size produced by best subset selection on the credit dataset. Okay. And what's interesting is that using CP tells us we should choose model 6, M6, whichever those 6 variables were. BIC, we choose the M4 model, and this is the, looks like M7 model. So apparently you want to maximize the R squared, but you want to minimize BIC and CP. Now, how do you actually even calculate these things? For a fitted least squares model containing D predictors, the CP, but what does P stand for? I would have expected it to be CD. You know, it's kind of like usually the left and right hand side should be related in some way. Maybe P is found in the RSS. Let's have a look. The CP estimate of test MSE is computed using the formula CP is equal to 1 over n RSS plus 2D sigma hat squared, where sigma hat squared is an estimate of the variance of the error term, epsilon, associated with each response measurement in 6.1. We're just referring to this error term over here. Think of it as the information that we sort of miss when only including these P predictor variables. No model will always no model can ever capture the true relationship. Can be anything. Okay, so for example, I don't know, if you're doing if it's physics and you have Newton's laws and all that, they're very good. They can get a, you know, put a human being on the moon and get them back, but they're perfect up to, I don't know, 99.99. There are always the variables that you haven't allowed for. And there's a footnote. There's also Mallow's CP, sometimes defined as this. This is equivalent, blah, blah, blah. Okay. So what is it doing? What is it doing? Well, you'll notice that this is just the training mean squared error. But the book describes, and I'll highlight it when I find another color, a penalty. And the penalty is this over here. Well, divided by n, I guess. To the training RSS, in order to adjust for the fact that the training error tends to underestimate the test error. Oh, this is really great, because if you've done a lot of overfitting, then you know, if it's a model that follows maybe too closely the data, then that will give you a very high variance and you get a very high penalty. Let's just see the formula very quickly. Just see the formula, and we'll read the details in our next session. So that's CP. AIC, basically the same thing, but it adds this. There's the BIC with some kind of logarithmic relationship. And this is also R squared. And then we'll do validation and cross-validation. And that will then take us to shrinkage methods. Quite a lot on shrinkage methods. And then we'll have 6.3, which is the dimension reduction methods. 6.4 is when we then considerations in high dimensions. Oh, look. So like in DNA, you're looking at 200 people, but you have on each person, you have information relating to 500,000, so 500,000 DNA type data. And 6.5 labs, and then 6.5 is labs. But we're going to stop over here.